Sir, I have a question regarding assignment one yesterday.
Yeah, maybe at the end of the class. Okay.
Okay, sir.
Yeah. Okay. So yeah, the recording has started. So in between, if you don't see the screen I'm sharing, just let me know, okay? Because I do not know what is happening at your end now. I only have one device with me today. So we'll start the important topic today, which is least squares. Okay. So So the topic that we want to start today is least squares. So what happens in least squares? We'll see, and then based on that, we'll see how to solve this least squares problem. What is the solution, and what is the geometrical meaning, and so on and so forth. Okay, so that is what we want to do. So let us start with this discussion. So okay, so the problem that we actually look at is okay, apparently I can get into my laptop. Just give me a second. I'll just see if I can do it. Just give me a minute. Okay, excellent. I can do this. So, okay. Okay, so fine. So let us start with this problem of least squares. Okay. So what generally happens is the following. We are trying to solve this problem ax is equal to b. Okay. Yeah, probably in tomorrow's class we are going to see where these least squares problems arise from. But let us start with this ax is equal to b. So far, what we have done, is existence and uniqueness, right? Existence and uniqueness for ax is equal to b. Okay, so we have seen this existence and uniqueness x is equal to b. Computations of solution, right? Computation of solution or solutions using QR, then LU, which is same as Gaussian, right? So these are the things that we have seen. And then we have touched upon one of the most important topics, sensitivity analysis, right? So these are the things that we have done. And what do we want to do is we want to continue this discussion further. So far, even though existence and uniqueness, in existence as uniqueness, we had considered A to be a matrix of the size A m by n, B to be the a vector of size Rn, and we were trying to find out x such that Ax is equal to B, right? Find x in Rm such that Ax is equal to B. That is what we have seen for existence and uniqueness, mainly for the computations and sensitivity analysis, both these parts. The systems that we considered were square systems, right? Mainly we considered this. Gaussian elimination, QR decomposition everywhere. We assumed that the system is square system. So now we again move away from this assumption and we ask this question. Suppose A is a matrix which is R m by n. Okay, A is matrix which is of the size m by n, and B is a vector which is of the size Rn. Okay, and the assumption, standing assumption that I'm going to have, throughout the discussion on least squares is that are columns of A are linearly independent. That's the assumption that I'm going to make. I'm saying that the columns of A are linearly independent. So if the columns of A are linearly independent, how would A look like? So A certainly can be square and invertible. Ax is equal to B. This is fine. Columns of A are linearly independent. Square and A invertible, correct, in that particular case. Or what does that mean? That means that I have a system where A is really a tall matrix, right? X is a vector like this and B is a vector like this, correct? Tall A, that means that M is greater than or equal to N and columns of A are linearly independent, right? That is how the matrix will look like. So what we are really going to focus on is this case, this general case where A has more rows than columns. So A is a tall matrix. A is invertible A has linearly independent columns. And then you want to solve this AX is equal to B problem, right? So this is something that you really are interested in doing. So Ax is equal to B, we want to solve. So when can we solve Ax is equal to B, right? A has linearly independent columns. When can we solve Ax is equal to B? So clearly, if B belongs to the column span of A, correct? If B belongs to the column span of A, then what does that mean? That means that B can be written as unique linear combination, as a unique linear combination of columns of A, correct? That so that unique linear combination basically is the solution X, right? So that unique linear combination is actually the solution of Ax is equal to B. But what if B does not belong to column span of A? Then clearly there does not exist any X in N such that Ax is equal to B, right? So A is Rm by N, X will be in Rn and B is in Rn, right? So that is the condition that we are taking. So it's a M by N matrix. So this is what you have, right? Correct. So this is the situation we are in. And in this situation, these are the columns of A, and this vector B is not in the linear span of columns of A, then there will not exist a linear combination, or there will not exist a solution X such that Ax is equal to B. In such a situation, what do we do? If if this thing is not solvable, what is the next best thing that we can think of? What is the next best thing that we can think of? Can anybody tell what will we do if we do not have a solution X? Then what is the next best thing?
Perturb and get a solution.
Sir, we can
Okay. Otherwise, yeah, Ashraf, go on.
uh, sir, we can find another vector b dash that could be somewhere near the column span of A, something like that.
Okay. Okay. So something similar to that we will do. Okay. So what we can do? Yes.
So
Yes.
we could maybe change the any one of the columns of A just by a little bit, not keeping it parallel, but just changing a little bit.
No, that you cannot change, right? A is something that is given to you, B is something that is given to you. Now you cannot change that data, right? So for example, A might have some information about some feature. You cannot really change the feature values according to your wish, right? That is not possible.
Yes.
So what will you do now? What to do in such a situation? So what we will do is something like this. You look at Ax is equal to B. You want to solve Ax is equal to B. Okay, there is no solution X. Okay, there is no solution X to this system of equations Ax is equal to B. So if there is no X such that Ax is equal to B, then Ax minus B is actually not equal to 0 for any X. Do you all agree? Ax minus B is not equal to 0 for any X. So can I choose a X such that Ax minus B is as small as possible? If not 0, then I want to push it as close to 0 as possible. Does that make sense? If it is not 0, then I want to push it close to 0 because I'm talking of the vector Ax minus B. You see, is a vector. What is the length of this vector Ax minus B? Can anybody tell? Suppose if A is in Rm by n, X is in Rn, and B is in Rm, then what is the length of this vector Ax minus B? Where does this vector belong to?
It will be in RM, sir.
It will be in Rm. So it is a vector of length m, right? So this is a vector of length m, and I want to choose a x such that Ax minus B as a m-dimensional vector is as close to 0 vector as possible, right? So as close to 0, what is the thing that we use for vectors to measure as close to 0 as possible? Obviously, the norm of the vector. So what I am going to do, I am going to plug in all possible values of x that I can plug in, right? So I will take any arbitrary random vector x in Rn. I will plug it in. I'll put it in here and I'll calculate the vector Ax minus B. Ideally, I will want it to be 0. If there exists a solution x such that Ax is equal to B, then actually Ax minus B will be a 0 vector. So norm of Ax minus B will be equal to 0. But typically when there does not exist a solution like this, then I have this problem. I will have Ax minus B. I will have Ax minus B not equal to 0, right? So what am I going to do? I'm going to look at this 2 norm. I'm going to look at this 2 norm and I'm going to minimize this with respect to x. What is the minimization of with respect to x means? Minimization of with respect to x means that I'm going to choose arbitrarily any value of x in Rn. That means that I'm going to choose any x in Rn. I will substitute it in this cost function. So this is a cost function, right? So this is the cost function in optimization. I'll put that value of x in there. I will evaluate Ax minus B. That is a non-zero number, right? I will do this for every x in Rn. I will have a lookup table sort of, right? So that lookup table, I will look at the minimum value of Ax minus B. That is when I reach closest to 0, right? That is when I reach closest to 0. If I cannot get 0, then I'll get next best thing to 0. What is it? That is something that will take me closest to 0. So that x I will choose. So the minimum value I will have, and sometimes I write this down as argmin. That means that the value of x which gives me minimum of this, that is equal to x hat. So for that particular x hat, say for example, Ax minus B, its 2 norm will be minimum, right? So that is what I'll do. So if I cannot find out the exact solution, if the exact solution does not exist, if it exists, then I can always find out the exact solution. But if the exact solution does not exist, then what do? I do the next best thing. I look at this particular thing, Ax minus B. So Ax minus B is actually called as residual. Okay. So this is called as residual vector. Okay. I denote it by R. Then clearly R is in Rm, right? It is an m-dimensional vector. So I can write down R as its components R1, R2 up to Rm, right? And what is this? Norm of Ax minus B whole, I will take whole square so that I can do away with square root. So this is basically equal to R1 square plus R2 square plus Rm square. And what are these Ri's in particular actually? These Ri's are actually, so R is equal to Ax minus B, right? So if R is equal to Ax minus B, so how do you get Ax minus B? So you have this, this particular A into X minus B, right? That is what you have. So how do you actually compute? If you look at the matrix vector multiplication, you are looking at the first row into this X minus this entry will give you R1, correct? That is what will give you R1. Then what is the next entry? R2 is the second row multiplied by this x minus this B2 value will give you R2 and so on and so forth, right? So this is how you are going to get R1, R2, Rn. So this basically, if you denote the rows of matrix A as A1, A2 up to A, how many rows will be there? M rows will be there, right? So if A1, A2, AM, small A1, A2, AM denote the rows. So I'll denote them by transpose, A1 transpose, A2 transpose, AM transpose. Then basically, what is this? This is A1 transpose into X minus B1 whole square plus A2 transpose X minus B2 whole square, so on so forth. This is AM transpose X minus BM whole square, right? So these are the residuals, right? These are the residuals. So if you think of matrix A as data matrix, if you think of matrix A as data matrix, then you have features along the columns. Every column is a feature and every row is a data point. It's a data point which is an n tuple. So A1 transpose is a data point, it's an n tuple. You find out the parameter x, so you do A1 transpose x, that's your prediction that you will give. And that prediction, A1 transpose x, basically, you are matching with B1. Similarly, for the second data point, A2 transpose, you are finding out the prediction A2 transpose x and you are matching it with B2. Similarly, AM transpose X, that is the prediction for data point AM, and you are matching with the observation BM, something that you observe. And what do you want to do? You want to find out an X such that this prediction A1 transpose X is as close to B1 as possible. A2 transpose X is also as close to B2 as possible. So you are looking at these differences, A1 transpose X minus B1, A2 transpose X minus B2, AM transpose X minus BM. You are taking squares and you are taking sum and you are asking, can I get the best possible X? So this X is actually the parameter, is nothing but the model that you are trying to find out, right? So the model in this particular case is linear. And what you are asking is that, can I find the best possible model X such that this residuals, sum of squares of residuals, is actually minimum? Does that make sense? This is something that is very natural for you as a machine learning or data science person to do. When you want to find a model, what do? You look at the residuals and you want to minimize the sum of squares of residuals. Sometimes you call it loss, sometimes you call it cost function. It's depending upon the terminology, right? And you want to minimize the loss, so to speak. So this is what you are really going to minimize. And because you are minimizing sum of squares, this particular method is called as least squares problem. Okay, so least, that means you are seeking the minimum. Squares, you have sum of squares and you seek least of that sum of squares. So you choose X such that this sum of squares is least. You choose X so that this sum of squares is minimum, right? So that is what we really are going to do. That is what we are really after, right? So this is something in which I can understand this least squares problem. So is this least squares problem through residual vector convincing? Like, does it make sense to ask such a question in first place? Are you all like on this with me? Is this clear? Okay, so if this part is clear, then I will look at least squares problem in a different perspective again. Okay, so there is a different perspective through which I can look at the least squares problem. So this is one perspective, minimizing sum of squares. That is something that I have. Now I can look at least squares problem from another perspective. Okay, so there does not exist a solution. There does not exist X such that Ax is equal to B. Okay, such that Ax is equal to B. In other words, B is not in the column span of A. Okay, so this is something that I am already assuming. Okay, B is not in the column span of A. Now, what does Ax really tell me? What does Ax really tell me? So suppose I have this matrix A and I have the columns of A written as A1, A2 up to AN. There are n columns, right? And the vector x is x1, x2 up to xn. So what does this Ax really mean? So this multiplication of Ax was taken from the row interpretation of matrix A, right? So you multiply first row with the x, second row with the x, mth row with the x. That is the row interpretation of matrix multiplication I was taking. Now, if I take column interpretation of matrix multiplication, then do you all agree that what I really have is this linear combination of columns A1, A2 up to AN? Xn An. So I have this linear combination x1 a1 plus x2 a2 plus xn an. I am looking at the columns of A, which are a1 a2 an, and I am taking linear combinations of columns of A. Is that okay? That is what I have taken. And now you see, when I look at this ax minus b whole square, right? This is what I am looking at. What am I looking at? What am I looking at is that basically x1 a1 plus x2 a2 plus xn an minus b, correct? I am looking at this. And suppose I say that x hat is the argument minimum of this ax minus b. What is this argument minimum of ax minus b whole square? Argument minimum of ax minus b whole square is, you first look at this problem, minimize over this. So you find out the minimum value of ax minus b whole square. And the minimum value of ax minus b whole square is achieved at one particular vector. That vector I am calling is x hat. Typically, there might be more than one vector. So typically this arg minimum is a set and you should write it down as x hat belongs to this. But I'll abuse the notation and I'll just write down x hat is equal to arg minimum. Okay. So x hat is a point at which this minimum is achieved. Okay. X hat is a point at which this minimum is achieved. So if I look at this x hat where the minimum is achieved, then what is the meaning of ax hat? The meaning of ax hat is I am looking at this linear combination x1 hat into a1, x2 hat into a2, so on so forth, xn hat into an. So this is the linear combination of columns of A that I have chosen. And apparently, this linear combination of columns of A is closest to the B, right? That is what I am really saying. So I look at all possible linear combinations of columns of A. All possible linear combinations of columns of A are these, right? If B were belonging to the column span of A, if B were belonging to the column span of A, then there would exist at least one linear combination of columns of A such that Ax will be equal to B. So this residual will be equal to 0. So you get 0 as the minimum value for Ax minus B whole square. That is the case when the solution exists. But if the solution does not exist, then no linear combination, if the solution exists, then no linear combination of columns of A will give you B, right? So now you are finding what you are doing now in least quest. Now in least quest, what you are doing is you are finding out that linear combination of columns of A. Which linear combination? X1 hat A1 plus X2 hat A2 plus Xn hat An. You are finding out that linear combination of columns of A, which takes you closest to the B, which takes you nearest to the vector B, right? So that is what you are really doing. So if you really see pictorially, if you want to understand this situation, then I will try my best to do this in 3D. Okay, so suppose this is the subspace. Okay, so you have to remember that this is the subspace. So this is the plane. So maybe I'll not draw like this. So this is the plane which passes through origin, right? So this is the subspace. This is the subspace of column span of A, right? So this is a subspace, that means that it's a hyperplane which passes through origin. So suppose if you think, you accept that this is a plane which is passing through origin, then how is the vector B looking? The vector B is looking like this. So this vector B is outside this plane. Okay, this vector B is outside this plane. So you cannot write down B as linear combinations of columns of A. That is what you are doing. But now on this plane, which is nothing but the linear span of A, on this plane, which is nothing but the linear span of A, you are finding out that linear combination of columns of A, meaning that you are finding out that vector, in the subspace column span of A, that vector you are finding out which is closest to the vector B. So there are many vectors here. Every linear combination will give rise to different vectors. This is one vector that you see. This is another vector that you see. This is another vector that you see, right? So there are so many different vectors that you see. But there is one vector here which might be closest to the B. Okay, you choose that linear combination which will give you a vector which is closest to B. That is another interpretation of least squares problem. Do you understand this interpretation also? So this interpretation arises if you look at matrix vector multiplication from columns of a point of view. And this interpretation, which is useful for us, residual vector interpretation, sum of squares interpretation, this is something that is really useful for us from data scientist point of view, right? So this is something that we will always like to do. So these are the two different interpretations. These are the two different interpretations of least squares problem. Are you okay with these two interpretations?
Yes, sir.
Do you follow what we have discussed? Both these things are clear to you. Any doubt in here? Yeah.
Sir, one question. So those colored lines, I mean, the ones which are not red. So do you assume that those are in the subspace? I mean, in the column span of A?
They have to be, right? Because you are taking
They have
linear
to be, right.
combination of columns of A, so they have to be in the column span. They have to be in the subspace. Unfortunately, the drawing is not very good on my part.
Okay.
I'm sorry for that.
Thank you.
But they all are on the plane, right? The plane is passing through origin. They are all on the plane because they are in the column span, right? You are taking some linear combination, and the objective is to find out that linear combination which will take you closest to B. If you cannot reach B through linear combination, then you will take that linear combination which will take you closest to B, right? That's all you can do. And that is what we really are interested in doing. This is all. Is that fine? Do you understand what we are going to do?
Yes, sir. Yes. Thank you.
So in both the perspectives, we are reaching the same conclusion that we have to find an x which goes as much close to B when we do AX. Is it that?
Yeah, you have to. Yeah, you are right. But what you have to say to be correct mathematically is that find that x such that x will go close to B. Not x will go close to B. Ax will go close to B. Okay.
Yes, sir. After
Yeah.
applying AX. Yes,
Yeah,
sir.
after applying Ax. Yeah, that's right. So choose that x which will take Ax close to B. And this is something, so this understanding, okay, this understanding on this particular page, especially, is something that is central to all data science modeling that you do, right? Any model you want to build, this is what you are really doing. So this, in general, A1 transpose X, A2 transpose X, AM transpose X, basically this is your model, right? So in your data science applications, what does this really look like? This looks like F of A1 transpose, F of A2 transpose. So F is the model that you are trying to build, AM transpose, right? So F is the model that you are trying to build, and A1 transpose, A2 transpose, AM transpose are actually the data points, right? They are the data that are given to you. And along with A1 transpose, you have an observation B1. What are you trying to do? You are trying to find out F such that F A1 transpose minus B1 matches as closely as possible, right? F A2 transpose matches with B2 as closely as possible. That is what you're doing. The model that here we have is the linear model, right? In general, you can have nonlinear models also. You will still try to minimize loss, which looks like this, right? In neural networks, that F will be a neural network. In support vector machine, that F will be something else. So you choose different applications, you choose different modeling techniques, you choose different model forms, this F will change. The model form that I have chosen here is linear model, right? Basically, that's what we are doing. Is that fine? What we are doing here and what is happening in least squares problem? Once you understand this, then we move on to the next part, which is about solving this least squares problem, right? How do we solve this least squares problem? So how do we solve this problem? So basically, what is the problem that we want to solve? We are given a matrix which is m by n, correct? We are given a B which is Rm, right? It is a vector in m dimension. A is Rm by n. What do we want to find out? We want to solve this problem, minimize over x in Rn norm of ax minus b whole square. Okay, I can minimize norm of ax minus b whole square or norm of ax minus b. It doesn't matter. Okay, I will still get the point at which the minimum value is achieved to be the same point. So calculation wise, sometimes this ax minus b whole square is easy to handle. So I will just take ax minus b whole square. And what is the standing assumption that we have made? The assumption is that columns of A are linearly independent. Correct? Columns of A are linearly independent. That is the assumption that I have made. And you want to minimize this. So if you see a minimization problem, what do you do? So how do you solve this problem now? If you see a problem which is a minimization problem, what will we do?
Differentiation.
Correct. What do we do? Correct. You are right.
Yeah.
Differentiation. You differentiate. So what will you differentiate with, and who will you differentiate?
Variable is x, so we will differentiate with x with respect to x.
And who do you differentiate?
Ax minus b.
So why do you differentiate? What will you achieve by differentiating?
Critical point.
Huh?
Critical point.
Critical point where the second
Critical
derivative
point,
is 0.
right? So once you obtain critical point, so do you get critical point just by differentiating, or you have to do something?
Equate it to 0.
Equate it to 0. So basically differentiating, we will say we compute gradient with respect to variable x of the cost function. That's what you will do. Equate that gradient to be equal to 0. Then you get critical points. Then when you get critical points, what happens after that?
Substitute that critical point in the function ax equal to b, and we'll find it double differentiative will give us a maximum exist or minimum exist.
So here, what is double derivative here?
Double derivative will not exist.
Now, why will double derivative not exist? What is the equivalent concept of? So now you understand that the differentiation is with respect to x. X is actually a vector. So basically the function that you are looking at, the cost function, is a function of several variables, right? So it is a function of several variables, x1, x2, xn. It is a function of n variables, in fact. So you have to take derivative with respect to n variables, equate it to 0. So you get a gradient vector. Then you get a critical point, which is a point in Rn, right? You will get several critical points possibly. Then what do you do at these critical points? You check the second derivative, right? But second derivative is a concept when the function is of one variable. What is the equivalent concept of second derivative here in calculus of several variables?
Hessian matrix.
Hessian matrix, correct. So you compute Hessian. Then what do you check for in Hessian?
Whether it is positive definite or not.
Correct. So you will check whether the Hessian matrix is positive definite or not. So if the Hessian matrix is positive definite, then you will get minimum. If the Hessian matrix is negative definite, then you will get maximum. And in case Hessian matrix is indefinite, some eigenvalues are positive, negative, then based on that, you will get something which is called a saddle point, right? So there are various issues here. So we have to calculate Hessian matrix and see what really happens, right? So that is what we have to do. So that is the calculus part of solving this, right? So we'll use this calculus, and using this calculus part, we will try to compute the solution to this least squares problem. Okay. So let fx, I will write down fx to be equal to norm of ax minus b whole square, right? So this is my cost function. So I write this cost function down in a little easy way, right? So what is the easier way in which I can write down this cost function? So you tell me if you all agree with me or not. So summation I is equal to 1 to n, summation j is equal to 1 to n, aijxj minus bj square. Is that okay? Can I write down ax minus b whole square like this? So aij are actually the ijth entry of the matrix, right? So a, so where a actually is aij, ij is ijth entry of matrix A. Is this okay? Do you all agree what I have done? So Aij xj, what I have done in Aij xj, you look at it, I is fixed, right? Aij xj, I is fixed. The running index is j. That means that I have fixed the ith row and I'm looking at all the columns ai1 x1 plus ai2 x2 plus ai n xn, right? So that is what I'm looking at. So I'm
Sir,
looking at the row interpretation. I'm looking at the row interpretation here, and I'm looking at the ith row, and I'm calculating what is ith
sir,
element of ax. Yes,
hello, sir,
yes,
BJ or BI? Sir?
it will be bj, right?
No, sir, it should be BI, right? Because uh,
Yes, sir.
You are
It should be
looking at
BI.
bi, correct? I am looking at ith row, so it is bi. I am looking at ith row, so it is bi, correct? So aij xj, I am looking at ith row. I am subtracting bi. I am looking at square, so that is my ri square, and I am looking at r1 square plus r2 square plus rm square. That is the outside summation. Okay. So this I hope everybody agrees with, right? So this is how I write down. And what I am trying to do is I am trying to find out gradient of fx, right? I am trying to find out gradient of fx. So what is gradient of fx? Gradient of fx is basically del by del x1 of fx, del by del x2 of fx. So I am differentiating with respect to x1, x2, del by del xn of fx, right? So this is what I am looking at. So the ith component I will denote by del fx, and the subscript k here actually denotes I am looking at del by del xk of fx, the kth component in this vector, right? That is the notation that I give. So I have to compute this gradient. So that means that I have to calculate these n partial derivatives. After calculating these n partial derivatives, I have to equate it to 0. So you see this vector, gradient vector, is a vector in Rn, right? So this is a vector in Rn. N. Okay, so that is something that we have to understand. So let us actually calculate this, right? Let us actually calculate this. So I'll write this calculation here. So gradient of fx, I will take derivative with k. So this is actually del by del xk of this cost function fx. So I will see. Okay, so this summation. Okay, so let me write it down. Summation I from 1 to m, and then we had summation j from 1 to n a I j x j minus b I square, right? This is what we have. So I will use the properties of derivative. So I will have this as I is equal to 1 to m, right? I is equal to 1 to m. Then I'll take derivative. So 2 times summation j from 1 to n a I j x j aijxj minus bi, and I will apply chain rule. So when I apply chain rule, what will I get here? I'll get aik, correct? I'll multiply this by aik. So this is how I'll compute derivative. I hope this is clear to everybody. So this I will write down summation I from 1 to m as 2 as it is. So this aik is the ith row kth column element of A. I can write this down as A transpose ki for the A transpose matrix kith element. And this summation which you see here is basically Ax minus B, the ith element. So this is Ri actually. This is what you have. And the reason to write it in terms of A transpose is that this summation I from 1 to m also can be written together in this form. So 2A transpose Ax minus B and the kth element of that. So gradient of fx, kth element is basically this. So if gradient of fx, the kth element is this, then what is the gradient of fx? So the gradient of fx, the vector, is actually 2A transpose Ax minus b. Correct? Is that fine? I hope you understand this calculation. If there is any issue, you ask me now.
So how did you write ax minus b of I?
So what is Ax minus b ith element? How will you calculate Ax minus b ith element? You will have ith row of A multiplied to x minus bi. Shubham, are you following?
Yes, sir.
So what is ith row of A multiplying to x? Do you get this? Summation of ai minus aij xj. This term you will get by multiplication of ith row of A with x. Do you agree?
Yes, sir.
So that's why I have written down x minus the ith element. Is that okay? Is that okay?
Yes, sir.
Yeah, that's all I have done. So it's just writing matrix multiplication. Here also I have used the same matrix multiplication logic and I get this particular thing, right? So gradient of fx is basically this vector. Okay, so if this is the vector, then what I'm going to say is the following. So let x hat be any minimizer of norm ax minus b whole square, right? That means what? X hat is actually argument minimum of norm ax minus b whole square, right? So x hat is one of the minimizers, say for example. Then what should x hat satisfy? Obviously x hat is a critical point. That implies that x hat has to satisfy gradient of fx hat is equal to 0. Is that correct? So if gradient of fx hat is 0, what does that mean? That means that what is gradient of this? So A transpose Ax hat minus B is equal to 0, which we can write down as A transpose Ax hat is equal to A transpose B. Correct? So if x hat is a minimizer, then x hat has to satisfy the condition that gradient of fx hat is equal to 0. If that is the case, then what is gradient of f at x hat? We know the gradient of f at x is given by this particular formula. So gradient of f at x hat will be given by this 2A transpose A x hat minus b is equal to 0. So 2 is a constant. I can cancel out. A transpose A x hat has to be equal to A transpose b. Right? So far, nowhere I had used the condition that columns of A are linearly independent. Now, if I want to find out that minimizer x hat really, then that condition is really important, right? So now, can I write this down so that x hat is equal to A transpose A inverse A transpose B? Can I write this x hat down in this particular fashion? A transpose A inverse A transpose B. Can I write it down? Why can I write it down? Why the inverse of A transpose A exists?
That gram matrix we are using.
Correct. So this A transpose A is a gram matrix, and we had already proven that gram matrix is invertible if and only if columns of A are linearly independent. So here we are using this condition since columns of A are linearly independent. Columns of A are linearly independent. A transpose A is invertible. So A transpose A is invertible. That means that I can compute X in this particular fashion. So the least square solution, the minimizer X hat that I have is actually A transpose A inverse A transpose B. But remember, A transpose A inverse A transpose is a spatial left inverse of A.
Pseudo
What did we?
inverse.
Yeah, correct. We call this pseudo inverse, right? So we call this pseudo inverse. So let us give this a notation also. So this pseudo inverse I'll denote as pseudo inverse of A, as you will see people denote it as A dagger. Okay, so this is like A dagger. Okay, so what is A dagger? A dagger is basically A transpose A inverse A transpose, right? And the least square solution, and the least square solution. So least squares I will write in short as LS. The least square solution to this problem Ax is equal to B is given by x hat is equal to A pseudo inverse B. So all you need to do is compute this pseudo inverse. Once you compute this pseudo inverse, then this is what you will get. So this is actually the solution x hat to the least squares problem that we started with. So I'm already writing the least square solution. Okay, so that is also something that you can notice and you can object, right? So here, what did we say? We said that x hat is one of the minimizers, right? X hat is one of the minimizers, so that x hat has to satisfy this. Okay, so these equations, actually are called as normal equations. Okay, so these equations are called as normal equations. And what are these normal equations? These normal equations are the equations that need to be satisfied by the minimizer of Ax minus B norm square, right? So if it is a least square solution, then least square solution has to satisfy normal equations. And now because A transpose A is invertible, you see that there exists only one solution. There is a unique solution to this equation. X transpose X hat is actually A transpose A inverse A transpose B, right? So that's all. So that's the only solution. So because that's the only solution, you have a unique solution to the least squares problem. And that uniqueness is guaranteed because we started with linear independence of columns. Because columns of A are linearly independent, then A transpose A is invertible. If A transpose A is not invertible, in this particular case, if the columns of A are not linearly independent, then you do not have a unique solution to this system of linear equations. So please remember, what is the size of A transpose A? Size of A transpose A is n by n. What is the size of A transpose B? The size of A transpose B is also n by 1. So it is a square system of equations. Normal equations is n by n square system, right? So it's a square system of linear equations, n equations in n unknowns, and those n unknowns are actually x1 hat, x2 hat, xn hat. So this actually solves the least squares problem. Is this fine? This is the least squares solution. Okay, so this is the calculus way of looking at least squares solution. There is another interesting way in which you can observe, you can see what is the least squares solution. This form, the calculation that I'm going to do, actually you might encounter this type of calculation in many statistical computations. Okay, so those statistics computations are typically done by adding and subtracting certain term in things like analysis of variance and things like that, right? So this type of thing you will observe there. So I'll just give direct verification or algebraic, okay, direct verification of least square solution. So what is the direct verification of least square solution? So suppose somebody comes and tells me that x hat is equal to this, A transpose A inverse A transpose B is a solution to the least squares problem. Okay, suppose x hat is equal to A transpose A inverse A transpose B is a solution to the least squares problem. Okay. So what is the least squares problem? Least squares problem is minimize over x norm of ax minus b whole square. This is the least squares problem. And what is the solution means? Solution means that particular x which minimizes this norm, right? So x hat is this. We want to verify this. Okay, verify that x hat is actually this solution. So what do? We actually start. So we start with this ax minus b whole square. Okay, ax minus b whole square. And what do? I do ax minus ax hat plus ax hat minus b. Okay, add and subtract this ax hat. That's what I do. And once I have this term as a, I have this term as b, then u plus v norm square, right? So how do I calculate this? So you check ax minus ax hat its square plus ax hat minus b its square plus 2 times ax minus ax hat transpose ax hat minus b. Do you agree that this is what I'll get? So this, if you recall, is coming from u plus v square is norm of u square plus norm of v square plus 2 times u transpose v. I'm using this identity to write this thing down, right? And what happens to this particular term? Observe this cross term that you have. So 2 times ax minus ax hat transpose into ax hat minus b. What happens to this term? I say this term is equal to 0. How? So this is 2x minus x hat, a transpose come out, ax hat minus b, right? So 2x minus x hat, and then you see I have already this x hat which is of this form, right? I am verifying that this is a solution. So x hat is already of this form. So this will be 0, right? So this will be 0. Sorry, this will be transpose. So the cross term is actually 0. And if this cross term is actually 0, then what are we left with? What are we left with is norm of ax minus b whole square is always norm of ax minus x hat whole square plus norm of ax hat minus b whole square, correct? So this is what I am left with. And now you observe, what do you observe here? You observe that this particular entity being a norm square is always greater than or equal to 0. This entity is always greater than or equal to 0. So what does that mean? That means that ax minus b whole square, this left hand side, this means that this number is always greater than or equal to this number. So for any x in Rn, this entity is always greater than or equal to norm of ax hat minus b. That means that x hat is actually minimizing this ax minus b whole square, because for any value of x, this cost function is always greater than equal to evaluation of the cost function at x hat, right? So that means that algebraically also, if you know the solution form, which is x hat is equal to a transpose a inverse a transpose b, algebraically also you can verify that this indeed is actually true. And uniqueness also can be guaranteed. So wherever the minimum is achieved, the equality is achieved, you should have this a into x minus x hat is 0, and because a has linearly independent columns, you will conclude that x is equal to x hat, right? So the minimum value is actually achieved when you have x is equal to x hat, right? So that's unique. There is no other value of x hat that will come. That will come because of linear independence of columns of A, right? So this is another way, algebraic way. This calculation I just showed because this type of calculation arises oftentimes in many applications. Okay, this type of calculation you always do, add and subtract a particular term, especially in statistics. This type of computations often arise. Okay, so this is something that I wanted to demonstrate, so I just use this. So I hope that this solution of least squares problem, how you obtain the solution, how you use calculus to obtain this solution, these calculations, all these things are clear. Okay, I hope so. This is very important. Okay, so now we have solved an optimization problem, and now you can ask why these equations are called as normal equations. So now what we will do in tomorrow's class basically is go back and look at this particular interpretation of least squares problem. Okay, what is this interpretation of least squares problem? This interpretation, so the calculus way looked at the row interpretation, right? So this is the row interpretation of matrix multiplication, and you looked at this row interpretation, and using that row interpretation you arrived at the solution. But there is a beautiful geometry there, that beautiful geometry that comes out because of the column interpretation, and that geometry will actually take you back to the same solution that we started, and that geometry actually justifies the name normal equations that you see here. Okay, so that is what we are going to do. So we are going to look at the geometry of the least squares problem, understand geometry, and then see where these least squares problems are really applied in data science, AI, MLDL. Okay, so that's what we really are going to do. So tomorrow, possibly, if we can finish geometrical interpretation and least squares data fitting, that's what we are going to do. So Ramnivas, do you want to say something?
Yes, sir. How did we make A transpose into Ax hat minus B is equals to 0?
Where?
While direct verification.
Direct verification. So A transpose A x hat minus A transpose, this will be equal to 0 because that is normal equations. No, see, you have assumed that x hat is actually equal to A transpose A inverse A transpose B. You have assumed that. So if you want, you can substitute that x hat here and you see that you get 0. Substitute that x hat. You are verifying whether this is a solution or not, right? So you start with this assumption that x hat is this. So you substitute for x hat here and you will see that you get 0. Is that okay?
Sir, x hat is the solution for the least square problem, not for Ax equal to B.
It's not the solution to Ax is equal to B. But I am not looking at Ax is equal to B either. I am looking at this whole part. A transpose into Ax hat minus B.
So without substituting the value of x hat, how did we conclude this is equal to?
Now, how can you conclude without substituting? You have to substitute the value of x hat here, and then you will see that it will be 0.
Okay.
So at this point, you substitute the value of x hat. That is your assumption. Right? So you are verifying whether this is a solution or not. So it is like someone came to you and said, okay, look, this x hat is a solution to the least squares problem. Can you verify? That is what someone is telling you. So now in order to verify, you started doing this. And at this particular point, you observe that if you substitute x hat in here, the value that that person wanted to verify as a solution, if you substitute, this term goes to 0. That's all I have done. Okay?
Yes, sir.
Yeah. So I think any other doubts?
Yeah, sir, for direct verification, how did you, what argument did you use for uniqueness? Could you repeat that, please?
So, so the left-hand side is always greater than or equal to right-hand side, the blue one. The blue box on the left-hand side is always greater than or equal to blue box on the right-hand side. Is that okay?
Yes, sir.
Yeah, the equality is achieved only if the red block becomes 0. Is that fine?
Yeah, yes, sir.
So if the equality has to achieve, that is the place where minimum will be achieved, the red box has to be equal to 0. Now look at the red box. Red box is A into x minus x hat norm square is equal to 0. So the vector has to be equal to 0 if the norm is 0.
Yeah, yes, sir.
That means that A into x minus x hat has to be equal to 0. That means that x minus x hat is 0. That's the only possibility because A has full column rank. That means that the null space of A contains only 0 vector. So x minus x hat has to be equal to 0. So any other vector for which this equality is achieved has to be equal to x hat. That proves the uniqueness.
Got it, sir. Thank you.
Okay, then maybe we'll stop here today. Yes.
sir, can you explain how did you get the subscript K? I think about 2 slides back in the last line of the derivation.
Here, subscript K. Yeah, so
Yes.
this is a matrix. This is a matrix that I'm looking at. So if you look this A transpose, suppose you call it B, and suppose this vector is Z, then do you agree that I am actually looking at this as BZ? So you have a vector, sorry, you have a matrix B and you have a vector Z. If you multiply matrix B with vector Z, what do you get? So you see the K index is constant here. That means that you are looking at the kth row of matrix B and you are multiplying vector Z to the kth row of matrix B. Is that okay?
Yeah. Yes.
So if that is what is happening, then what is this in the matrix vector multiplication BZ? So because this is a matrix vector multiplication, you will get a vector. You are looking at the kth component of this vector by this sum.
Yep. Yep. So this is okay. So I thought
that
K is the column.
Component. No, that is the kth component. There is no column. This is a column vector. In that column vector, you are looking at the kth component. That's what you are doing.
Okay, thank you.
Sir, one more thing. Shouldn't we write subscript at A transpose? Because that is the row that is getting multiplied with the vector Ax minus B.
So kth row of A transpose. Kth row of A transpose is getting multiplied to the vector Z.
So
is that okay?
So shouldn't we write K at A subscript for A transpose? Or
so if I take B is equal to A transpose, then what I really mean is BKI is A transpose KI. So if you have problem with the notation, I don't know. My notation, maybe it is wrong, but this is what I mean. Is that okay? Like, what I mean is kth row of A transpose is getting multiplied to Ax minus B. That's all.
yes. Okay.
So if that is clear, then I think what you want to say is clear. Maybe my notation is bad. I may have used bad notation. I don't know, but this is what I thought I will use. So, I mean, I won't agree with this notation for sure. AKI transpose. Is this what you want to write?
No, sir. In the line 2A transpose multiplied by Ax minus B subscript K, instead of that, 2A transpose subscript K multiplied by Ax minus B.
No. So this is actually the entire matrix, and I'm looking at the kth row of that matrix. No, that is what I'm doing.
Yes, sir. I got it. Okay.
Yeah, that is what I'm doing. Okay. Yeah. Okay, then we'll
Sir, sir, actually, I got assignment, sir. Yesterday assignment.
Wait. Yeah.
Yes, sir. Could
So
give.
we'll stop here today. See you tomorrow.